That has struck. A recent example of the Tennessee floods in various resolutions. These are the more traditional methods of using airborne imagery to assess geospatial data. Of course, higher accuracy data sets. Also in an oblique way, of course, for more localized applications, like also recently the tornadoes that have hit Alabama. And lastly, and I think this is where my starting point is, of course, LiDAR technology to really monitor buildings and so forth. LiDAR technology uses a laser that emits a light source that gets reflected, and of course with this you can monitor not only digital, or you can not only create digital elevation models, but you can map buildings in such a way. What we propose now is to go back one step and use imagery to match pixels and create a digital elevation model based on imagery. This is not a new technology, but what is new is the speed with which we can do this today, and of course the accuracy we can achieve with these technologies. Here an example from Switzerland, which was a collaboration with the Avalanche Institute to monitor snow depths. And with this technology on the left-hand side you see the digital elevation model that is derived from this imagery. On the right-hand side you see this digital elevation model enhanced with an intensity image that shows now features. You can see these things here are ski slopes, of course, that was very known for skiing. But of course it's also an avalanche high-risk area. With this technology you can now map large areas without having to send people in the field at an accuracy that you normally would only get with terrestrial laser scanning methods. So we're talking about pixel accuracy. Of course, there are traditional applications such as mining and to monitor mine stope stability. And this example gives you sub-pixel accuracy in a mine in Australia. And with that, of course, you almost have auditable results that you previously never had. The next logical step would be to use such technologies or such point clouds that are derived from imagery in urban mapping. In this case, an example from Italy. Of course, you can now extend it over large areas. But what I really want to get at is the next example. And I think this showcases very much where we see the potential of this technology. With these new ways of extracting these pixels by pixel matching image data and generating a point cloud from this image data, you get very, very high accuracies and very high point densities that you don't get with LiDAR. You can see in this image here, this is a house with a roof. Based on this technology, this is no editing of the datasets. This dataset comes straight from the sensor and you have a very good accuracy and a very good image of this house type itself. When we now combine this with the image, and I do apologize that this is a little bit dark, but you suddenly can add features to this which help you with the interpretation of these datasets. And of course you can see here in this case we depict even handrails that are going over pedestrian areas. So the accuracy of this unedited data set is very, very high, and we reach point densities of about 300 to 400 points per square meter. This is a factor much higher than what you get from LiDAR. And I think the key here is, particularly for disaster risk reduction, we can extract these points very, very quickly. We can extract these points in a normal workstation of about 20,000 to 40,000 points, which means that even larger areas, we do have one customer who recently mapped the area twice of Switzerland in mapping. When I talk about mapping, this is not in an emergency response environment, but this is in a traditional mapping to create a map layer that could be used in the future for an emergency response. Twice the area of Switzerland has been mapped in just under 1 month, which is phenomenal in terms of the accuracy, the speed, and so forth. And I think that's where it becomes very attractive, because image data is available anyhow. Any one of you who's been using image data in interpreting disasters, in assessing disasters, in assessing risk areas is very familiar with the image data. So with these technologies you can go one step further. Of course, and I think this example is very impressive, you can now go down to the detail of each house, of each roof, which would lead you to the next level of reconstructing. If you have a base layer in your data system that contains this information and disaster strikes, you are able to use this reference layer and combine it with a new layer in almost no time to really immediately, automatically detect the change that has happened in this area and use this to actually assess the quality of the change in this area. Where I think the departure is from the traditional methods where we're using LiDAR data and then overlay an image over this LiDAR data, over this DSM, is that we are now generating from this imagery a point cloud that already contains the value of the spectral information from this imagery. In this case, on the left-hand side, you see the nadir view of a point cloud with imagery, and on the right-hand side, you see the 3D model. Here with the rooftop, very clearly depicted, and even in the bottom here, below these boats, you can see actually bathymetric information. This information is highly accurate. We're talking about 5 to 7 centimeters in accuracy, height accuracy. So highly accurate information that you can use going forward. Of course, you can use this now in a multispectral way as well. You can generate this information not only in the traditional RGB, red, green and blue, which we humans see. You can actually extend that into the near infrared, which gives you additional information which is often used for environmental applications. Again, this image here shows very clearly that we are not draping imagery over a DSM, but we are rather generating a point cloud with already multidimensional information in it, which is why we call this the info cloud. Info clouds can have multi-dimensions. They can have 3, 4, 5 and more dimensions. And of course, with those info clouds, we now have the opportunity to really extract that information very fast. I just give you an example. Maybe you can see that these are people on the roof on one of those image data sets. You can just skip through the next few images. You can see that, of course, here we are now generating, even over those people that are lying on a sun chair, we can actually generate a very highly accurate digital elevation model. This data set has been generated overnight and over the city of Lucerne. You know the city of Lucerne, of course, most of you who are here in Switzerland have been to Lucerne. Lucerne takes about 2 to 3 hours to acquire in this kind of environment, and we take about a day or two to process the data in this accuracy. And I think that's something which is rather innovative. We can go through the next slides. We can of course tin those information as well, and you can see here towels and so forth. And we're going to the next slide then. And what we're trying to get at, and we are at the beginning of this technology, but if you compare this, for instance, with data from AIDI, which has high density buildings, and where the big question is how many houses are still standing, where have these houses been standing previously, and where are they standing now, or where have they been destroyed? Where are property boundary lines? If you have this kind of information, and you can generate with the same imagery highly accurate 3D point clouds, then I think for these cases, or even when you zoom in, for these cases, this additional information can really help in the emergency response. There is no additional cost of data acquisition because this data has been acquired anyhow. Of course, the big challenge that we see here forward, and hopefully there are many that are interested in these data sets, so we are looking forward to really work with you and with the various scientific teams around the world that have access to such data sets to generate more of those info clouds. And to do that, we need to manage these huge sizes of data. As anyone who is in data management, with billions of point clouds, you're generating terabytes of data, and these data sets needs to be managed. In this case that we show here, this is an example from Chile, where we generated a whole range of data sets, we hosted a whole range of data sets that then were shared around among the scientific community around the world. We are working the traditional way. We have an image data layer, we have an information layer, we have a GIS layer, we have a derived information layer. We combine those and share those around the world. Going forward, this traditional approach of capture, process, sharing and delivering will be somewhat disturbed because this middle part of process, thinking in layers, will be revolutionized by this info cloud, because this info cloud does not contain several layers. It is one point to which several attributes such as gray values, radiometric values and even interpreted values can be assigned. So with this, I think this is where the future gets very, very interesting going forward, and where we hope to work with you more to interpret those data sets, to generate those data sets and see how they can be used not only in disaster risk reduction, but of course also in emergency response. And we hope that going forward, this info cloud will establish itself as one of the tools that can prevent a lot of the things that of course have happened recently, and if not prevent, at least help us to alleviate the damage from that much faster. Thank you very much, and if you would like to have more information, you can go to our website, hexagongeosystems.com, or join us. We have an upcoming conference that talks about these topics, info clouds and other tools that can be used in June. Thank you very much.